Hey guys, this is going to be your 5.1 lecture. Uh, 5.1 is a pretty short section that just sets up most of the ideas of the rest of the chapter, this idea of an integral that we're going to get to. So for right now, we're going to estimate the area under a curve. And so the area under a curve, we're going to define it as the area between the curve and the x-axis for some predetermined period on the x-axis. So we'll have a nice base, we'll have well-defined endpoints, but our height curve can be different than usual. So it's not just finding the area of a rectangle or a triangle or something like that. And what we're going to do is we're going to estimate this area by drawing rectangles. So we'll divide up our region, and the first thing, let me switch to my red pen. First thing we'll do is actually divide it only into one rectangle. And so the rectangle that this guy fits in best has area 1. So we know the area of under this curve is less than 1. Then we could divide up the region into 2 rectangles. And so this one here is the rectangle that my curve fits completely under. And then I get that one there. And this is called the left endpoint method because I'm setting the height of my rectangles as the left endpoint on my interval. We can also, and we will in a minute, do this with right endpoints. So now I get the area of this guy is equal to 1/2. That's the base of the first rectangle times 1 plus 1/2 the base of the second rectangle times the height here. Well, the height here is determined by the curve, so that's going to be 1 minus 1/2 squared. So this is 1/2 plus, let's see, that's going to be 3/8. So this is all 7/8 or what is it, 0.875, I think. And so this is the area with one rectangle. This is the area estimate with 2 rectangles. I'm going to have to draw the shape again to estimate it with 3. Matter of fact, let's skip 3 and go straight to 4. We could do it with 3, but if I go to 4, then I don't have to redraw the shape. Let me actually redo that in blue. So there's the first rectangle, there's the second. For this purpose, we're assuming all of our rectangles have the same width, have the same base. That just makes the calculations easier. It doesn't actually change the estimation. So now we're doing our estimation with 4 rectangles. And the first one will have a height of 1/4, sorry, a base of 1/4 and a height of 1. The second one will have a height of 1/4, and that is actually my x-coordinate there. So the height of this will be 1 minus 1/4 squared. And then this guy has a base of 1/4, and then his height is 1 minus 1/2 squared. And then, so that's the third rectangle, and the fourth rectangle is going to have a base of 1/4 and a height of 1 minus 3/4 squared. So that's 1/4 plus 1/4 times 15/16 plus 1/4 times 3/4 plus 1/4 times, okay, a little tricky here, that's going to be 9/16. So I think that is 7/16. And if we add all of this up, we get 0.78125. Now, I'm actually going to pull from page 303 here. This is the upper sum column of that table, and so they did it for 2, they did it for 4. and they do it for like 16 and 50 and 100 and 1,000. And so like their A1000, that would be 1,000 rectangles here, evenly spaced. So all of them with a width of 1/1000th and a height equal to the function value at that left endpoint of the rectangle. They get 0.6671665, approximately, probably. And so you see, our estimates were decreasing, and if you read, let me pop that up on the screen, I think you can see it. If you check this out, what we have is as the number of intervals increase, we seem to be converging on something around 2/3, right? We started here, they're getting closer and closer together, and it doesn't look like they're dropping below 2/3. And we could look over here to the lower sum, and you see that they're rising up to somewhere around 2/3. Now I'm going to show you how to do that lower sum. So what they're calling the lower sum, I'm going to call the left endpoint method because, I'm sorry, the right endpoint method, because on this particular problem, the right endpoints are going to give me an underestimate of my area. So if I just draw my curve again, something about like that. There's one, there's one. So now if I do this with two rectangles, I get the really weird look, and there's one rectangle, and there's the second rectangle. And the area with two rectangles here, that's going to be, my right endpoint there, remember, was 3/4. So that's 1/2 times 3/4 plus 0. So that's just 3/8 or 0.625. No. 0.375. And then if we were to do this with 4 rectangles, let me switch colors, then I get 1, 2, 3 subdivisions. Now remember, this is the right endpoint method, so the top of the rectangle needs to be at the right endpoint there. So then I get A4 equals, so that'll be 1/4 is the width of every rectangle, and that first one is going to be 1 minus 1/4 squared. We're going to know what these are from earlier in a second, plus 1/4 times the height of the second rectangle is, we just know that one is 3/4. We've done that one. This is the third time now. And then the height of that rectangle, so 1/4 times that, it's I'm going to pull it up from the previous page. That's 1 minus 3/4 squared. So that's just 7/16. And while we're at it, this one is going to be 15/16. And then the fourth rectangle has height 0, so plus 0. So this is definitely giving us an underestimate. And that last rectangle will always give us a height 0 here because the right endpoint of the interval is at 0. This wouldn't be true if our curve were different. When we add this up, we get 0.53125. And we see, like I said a minute ago, that these tend upward. So at 16 rectangles, we're up to 0.63 and change. And by 100 or 1,000 rectangles, we're up really close to 2/3, but just below it. And so my overestimate seems to be decreasing to 2/3, and my underestimate is increasing to 2/3. And of course, 2/3 is just a guess. I mean, how would I know if this was not 0.66666, and then in the 1,000th decimal place there was a 9 instead of a 6? I mean, I'm not going to know that. But we will get a method to do this and compute those limits exactly before it's all said and done. There is nothing special about using the underestimate or the overestimate or the right or left endpoint. They do another example, and I'm not going to go through it because it's very similar to these, where they use the midpoint. And the truth is, when your rectangles get narrow enough, you can use any height inside that rectangle, because you can see that as they get closer and closer together, there's not very much of a difference in that height there. And since they're getting tinier and tinier, our intervals here, the variation in the height is also going to decrease for any reasonable function. And so that's estimating area under a curve. You just draw the appropriate number of rectangles, compute the heights, compute the common width, and do a finite sum. We're just adding up a finite number of terms. Now, the finite here is a tip-off that when we don't want to estimate any longer, when we want to actually know, we're going to have to take an infinite sum. But that's okay, because when we're taking an infinite sum, what we're really doing is taking a limit of some finite sums. So very calcy sort of thing to do. That's 5.1.